Okay, so this is a video just to kind of introduce parametric equations. And as I mentioned in class, one thing that parametric equations can be used for is relating to particle motion. Another thing might be when we start talking more about vectors. I'm sure you've worked with vectors in physics, and we'll talk about those just a little bit later. But today is kind of the pre-calculus behind parametric. And that is just kind of drawing parametric equations where you have two different equations. So let me just kind of give you an idea. What we've been doing in the past has been what we call plane curves, in terms of x and y. And I don't normally read to you from a textbook, but this is such a really good explanation, I think it's worth looking at. So notice it says, until now, you've been representing a graph by a single equation, involving two variables. In this section, you'll study situations in which three variables are used to represent a curve. Here's why three variables are important. It says, consider the path followed by an object that is propelled into the air at an angle of 45 degrees. Okay, and so we're given an initial velocity of 48. The object travels along the parabolic path. So I can graph this equation of a parabola. Forget the arrow that's on there, and all I'll see is this parabolic shape, if that's what I graph. However, and here's what I want you to notice. This equation does not tell the whole story. Although it does tell you where the object has been, it doesn't tell you when the object was at a given point. So in other words, this can tell me, like, let's say this represents the path of a rock. I throw a rock into the air, it moves along this parabola and then lands over here on the ground. So at any point in time, like maybe at this point right here, I can tell you how far the rock is away from me, and I can tell you, so that would be the horizontal distance, and I can tell you how high in the air it is based on this equation, but I can't tell you at what point in time it is that far away and that high. So this gives me a horizontal and a vertical change, but doesn't tell me anything about the time that those changes happen. Okay, so I'm right here. It says to determine this time, you can introduce a third variable called a parameter, and the parameter is the t, by writing both x and y as functions of time. So instead of writing y as a function of x, we're going to have two equations, one for x and one for y, and they're both going to be functions of time. Those are what we call parametric equations. Okay, so if I look at this parametric equation, I have x equals, here's my one parametric equation for x, the 24 root 2 times t, and this is my parametric equation for y. These two equations, and we'll show you later how we get these two from the original, these two equations will tell me, this is going to tell me how the horizontal change based on time, this is going to tell me the vertical change based on time. Okay, so that's kind of what parametric equations do for us. They give us just a little bit more information. So just the basic thing we're going to do today is talk about how do we graph parametric equations. And one thing about parametric equations is that direction matters. It's important to us which direction this curve is going. So in order to do this, basically we create a big old table of values. I've got parametric equations. This one is my x. This one is my y, and so I'm going to create a table that's going to give me the value of both x and y, and those are going to be all based on the time, the parameter. So for example, notice in this case, because we're not talking about throwing a particle in the air, or I'm sorry, throwing a rock in the air. So the t is just my parameter, and t doesn't necessarily represent time. So that's why they're saying, hey, in this case, let's let t, our parameter, go from -2 to 3. So if t is -2, if I plug that into the x, I'm going to have, let's see, 4 minus 2 is 2. And if I plug -2 into the y, -2 over 2 is, I'm going to have -1. And so what that means is, for t equals -2, I have the point to -1. So if I graph the point to -1, so this is the starting point for this parametric equation. And then if I plug in -1 for t, I'm going to have, let's see, -1. You all can do the math and check me, and I think -1/2. So notice I'm just plugging t into the x equation, and then I'm plugging t into the y equation. So then I progress to the point -1, -1/2, which would be right here. Okay, so I'm kind of going backwards because I'm progressing in the order of t from -2 to -1 and so on. So I've gone from, let me make this a little bigger just to show you, I've gone from that first point to the second point, and I could kind of show an arrow to show which direction I'm going. Okay, let's come back to our table of values, and then I'll put in a 0 for t. So that's going to give me -2 and 0. So then I get to the point -2, 0. So -2, 0. I'm right here. So let me kind of get rid of this right here. So basically, I'm going in this direction, right? And then I'll go to +1, which will give me the point -1, 1/2. So then I go back here, so then I make this turn and I start heading back this direction. And then I go to 2, t equals 2, would give me the point 2, 1. And so from there, I get to this point, so I progress there. Notice my arrows are showing the direction of my graph, and then from there, I go to t equals 3, which is going to give me the ordered pair 7, 3/2. So then I go all the way out to 7, 2, 3, 4, 5, 6, 7, and 3/2 is right here. So then I keep going, and I stop right there at that point. So the thing about what I've done is I've graphed the parametric equations, but what it's done for me is not only told me the shape of my graph, but the direction in which we're graphing. Okay, let's try another one. Letter B. So I'm going to do the same thing. I'm going to set up my x and y equation. X and y, and it's all going to be based on t. And this time they say, let's see, they don't tell me parameters for t. So how about we talk about a full circle, 0 to 2 pi. But I don't want to do all of my angles. I'll do it at 0, pi over 2, pi, 3 pi over 2. That's good enough to give me the representation of a full circle, right? And then to 2 pi. So let's see if we can fill in. If I put in a 0 for t in the x equation, I'm going to have, let's see, 3 plus 2 is 5. And if I put a 0 into the y equation, I'm going to have -1. So I start at the point 5, -1, right there. And then pi over 2, if I plug a pi over 2 in for t, I'm going to have 3 pi over 2 in over here is going to be 2. So then I go to the point 3, 2, right here. I'm at the right point. 3, oops, that was 3, -2, sorry. 3, 2, 1, 2, 3, right here. Sorry about that. All right, so I'm headed up this direction. Okay, and then at pi, I'm going to have, what's that going to be? 1 and then -1. So then I head over to 1, -1. So basically, I progress through that point. I make the turn. I head this direction. And then at 3 pi, if I plug, I'm sorry, not 3 pi, 3 pi over 2. If I plug in 3 pi over 2, I'm going to be at the point 3, -4. I'm just using my unit circle. So then I go to 3, -4. So I'm heading back down this direction. And then at 2 pi, if I plug in 2 pi, it's going to take me to 5, -1. And if you notice, 5, -1 is the point I started with. So if I follow this along, basically it's mapped out this ellipse, I think. Okay, so one thing we can do is we can draw the graphs based on the parameter. The other thing we can do is we can come up with what the actual rectangular equation would be. You know, the old days, you know, yesterday, if I were to be graphing this kind of sideways parabola. And the way we do that is by what we call eliminating the parameter. Eliminate the parameter. Meaning, get rid of the t and take it back to just x and y. And the way to do that is to pick one of the parametric equations, x or y, it doesn't matter, and solve for t. I think it would be easy to take the y equation and solve for t, excuse me, because then we would get t equals 2y, and then take that and plug it into the x equation. So in place of the t in the other equation, I'm going to plug in 2y, and so I will have x equals 2y squared minus 2. And if I clean that up, I've got x equals 4y squared minus 2. And you may or may not remember from your pre-calculus / algebra 2 days that if there's a y squared, it represents a parabola that's like turned sideways. You know, if you're not sure about that and you want to go ahead and solve for y, because that's what you're used to. If I solve for y, I'm going to have, let's see, y squared equals, add the 2, x plus 2, getting rid of the 4 would be like a 1/4 out in front, and then y would be plus or minus the square root of, I could say, you know what, I'm going to go ahead, because I'm going to take the square root of both sides. Let me show you here. Because I'm going to take the square root of both sides. I'll go ahead and say that the square root of 1/4 is 1/2. So I don't have to have that under the square root, and then I have the x plus 2. Well, does that look like the square root graph? Yeah, it does. Notice this part up here on the top. This part up here on the top is the positive square root graph. This part down here is the negative part of the square root graph. So you can see how I can turn those parametric equations into a rectangular equation, which is what we're used to. Okay, so let's look at letter B. Can we eliminate the parameter on this one? Well, do you remember from your Algebra 2 and pre-calculus days what the equation of an ellipse looks like? Isn't that the kind where you have both an x squared and a y squared? What I remember from Algebra 2 is like x minus h squared over a squared plus y minus k squared over b squared equals 1. Remember that? All right, well, let's just see if it turns into that. So what we said was solve for t. Oh, no. How am I going to solve for t if it's in a trig function? Okay, so what we could do is we could use our identities. So let's do this. I'm going to take the first equation, and I'm going to solve for cosine. So I'm going to get cosine of t equals, let's see, that's going to be x minus 3 and then over 2. Okay, then I'm going to take the y equation and I'm going to solve for sine. So sine of t equals y plus 1 over 3. And isn't there an identity that says sine squared plus cosine squared equals 1? Remember that identity? Sine squared plus cosine squared equals 1. Well, if that's true, that means that x minus 3 squared over 4 plus y plus 1 squared over 9 equals 1. Now, I know I switched them because the x minus 3 was the cosine, but they're being added, right? So order doesn't matter. And you may or may not recognize it, but doesn't that look like the equation that I have written over there? That would be the equation of a parabola. And you may or may not remember, but back in the day, remember the number on the inside, your HK, that was the center. So this would be an ellipse that has a center of 3, -1. Does this have a center of 3, -1? Well, darn it, look at that. And remember how the 4, the number under the x, represented how far you go in the x direction, but remember that's like an a squared, so you would go 2 units left and right. Look, 2 units both left and right. And then doesn't this 9 represent how far you would go up and down? So that's your b squared, so the b is 3, so you go 3 units up, 3 units down. Now you may not remember all of that ellipse stuff, and so you're all freaking out, but you don't necessarily have to remember that. But what we will be doing is we will be doing this eliminating the parameter, where you take the two parametric equations and bring them back down into just one rectangular equation. So basically this is what we got when we eliminated the parameter. This is what we got when we eliminated the parameter. All right, and that's what the homework is. It's just practicing filling in that chart, drawing the graph, and then seeing if you can eliminate the parameter. All right, so it's just that one page, 229. Good luck with that.